Good afternoon. I, Dr. Purvi Bharadwaj, Associate Professor, Department of Physical Science, Rabindranath Tagore University, Bhopal, welcome our Vice Chancellor, Sir, Dr. Brahma Prakash Petia ji, our today's keynote speaker, Dr. Sadhna Singh, Professor and Head, Department of Physics, Barkatullah University, Bhopal, all the Deans, HODs of RNP University, all faculty members and dear participants. Welcome you all to the Faculty Development Program on Recent Advancement in Pure and Applied Physics. This virtual meeting offers a way for everyone to participate in and enjoy the same benefits as like physical conference without the travel and expense. Online conference and meetings are an amazing way to share and learn through networking. The aim of the meeting is to connect experts and upcoming researchers worldwide on this virtual platform and explore the contemporary approaches. Our agenda is to help the audience to gain a better insight into the advancing technology in a great manner in the field of physics. I invite our Dean Ma'am to welcome our Vice Chancellor, Sir, Dr. Neetu Paliwal Ma'am.
हेलो आवाज आ रही है मैम आवाज आ रही है हेलो
Yes, ma'am.
ओके ओके गुड आफ्टरनून टू ऑल On behalf of Faculty of Science, RNTU Bhopal, first I welcome to Honorable BC Sir for giving their valuable time for us. I would like to heartily welcome to today's speaker, my guide, mentor, Dr. Sadhna Singh Ma'am, Head of the Department of Physics, Barkatullah University, Bhopal. We are very grateful to you, ma'am, for accepting our invitation. At last, I would like, thank you, ma'am. At last, I would like to welcome all faculty members, participants, for attending this online 5 days faculty development program, Recent Advancement in Pure and Applied Physics. Thank you, ma'am. Over to you, ma'am.
Okay. Thank you very much, ma'am. I invite our Vice Chancellor, Sir, Dr. Brahma Prakash Petia ji, for saying some words. Hello.
Welcome to you, sir. Hello.
Welcome, sir.
Thank you. Am I audible?
Yes, sir. Yes, sir.
So, Dean Science, Dr. Neetu Palwal ji,
Thank you, sir.
Dr. Sadhna Singh, the head of the physics from Barkatullah University, Professor Jyoti Rawat, head of the department and the convener, Dr. Puri Bharadwaj, the faculty colleagues from RNTU, as well as from the other participating universities and colleges across India, including research scholars. Though I am not from the science background, physics or chemistry, but in engineering we have learned certain things related to physics. And particularly when we talk about the engineering courses, this is basically a lot of from the applied physics. So there is not much difference between the applied physics and the engineering aspects. When we look at about 4 years since that Galileo came with a electromagnetic astronomy, and when we look at the other changes in our understanding of the universe, it will come from the light, X-rays, gamma rays, radio waves, etc., etc. Now we can speculate that there are going to be enormous changes similarly and particularly simultaneously also over the next 400 years with the what to call it gravitational astronomy. So the science is not static, it is dynamic, it is changing. But the time period may be a little more because we are not able to run with the time. The changes are the only constant factor that everybody talks about. And it will reference for the centuries to come and not just for the decades. Now, the international collaborative efforts are absolutely critical to its success because no country can do it alone. So the techniques they devise to solve the Einstein's equations, which I look at it, and then to predict the shape of the waves, which were absolutely critical. The technology transfers came from Moscow. The complicated aspects of the suspension systems came from Glasgow. Much of the laser technology came from Germany. Austria too was contributed to the high laser power optical issues. So this was truly absolutely is an international collaboration. No country alone can do the research which is for the betterment of the mankind. Where we also have to inspire our students as they need to become enthusiastic first into the applied physics. Because simply teaching theories has no meaning unless students get involved not by brain but also by the heart. Then the natural human curiosity will drive them to learn and to go for more research. We as teachers have to contribute to generate interest among the students through the books, science fiction movies, and giving challenging assignments. You challenge them, then they will do it. I think that will have some impact on the enhancement of the students' interest in the applied physics or the physics then we call it, which is just a phenomena of the what you call it is not converted into the applications. The best way to generate enthusiasm about learning science in general and particularly applied physics in particular is perhaps to explain the theories behind many of the natural phenomena and associate those natural phenomena that is around us, like very simple thing, why the sky is blue. Simple ask the question and explain them. Then the students will start taking interest. Or whether the space is blue or black, or some questions which can be interesting, like if I want to lift 150 kg of the weight somewhere in the planet, where should I go? So the gravitational theories in the different planets will come automatically. So in other words, by helping students to understand the natural phenomena around them, in the daily life around them, using the theories, may be in a position to influence them to a science in general first and to the applied science or applied physics at a later. We have to foster curiosity among the students, faculty, researchers in universities that they should encourage to pursue the things just out of the kind of curiosity. The curiosity has to be developed, which surprisingly often does lead to a practical applications. They may become a very good scientist. So today, the physical boundaries as well as specialized domains are disappearing. We can get in touch any scientist, any other students throughout the world. So can we have some kind of integrated application oriented domain which is getting the priorities? We can have the students from the different parts of the world working on the same problem, and then they will come up with the very good suggestions as such. It is the physicists work with biology. This is also a amalgamation of the with the other working areas. Physics or applied physics cannot be seen in isolation. We have to see the applications in biology. Engineering is already an applied physics. Lot of things are there. And engineers, they have to be huge impact on physics. One secret of the success is to foster cross-disciplinary interactions. That is what I'm trying to advocate as such. The second secret of this hiring absolutely superb scientists. We should not compromise in the research with a mediocre researchers. We require brilliant scientists to be there, superb scientists, and then these resources will be excellent, and we are going to have an excellent research in this field. We in India have to create more, lots of merit-based opportunities for our scientists to interest with the scientists with the other countries.
So if I need to, you know, I think all four are necessary. You cannot throw it anyway.
I think some voice is coming. I am not
So
getting
this is
it.
another way of identifying it.
Either somebody has not mute the mic,
Yes, sir. Yes, sir. Yes, sir. मैं message कर
or
दूँगी.
it is instructions to me. I getting confused.
Sorry, sir. Sorry.
Lot of
Please
why,
जो भी है माइक अपना बंद कर लीजिए.
why you're
रमन
doing
अय्यर
Manoj
सर.
Sharma
अय्यर
sir.
सर.
Manoj Sharma sir.
अय्यर सर.
interesting, or it's just that you
अय्यर
are
सर को बोल दीजिए. अय्यर सर आप माइक बंद कर दीजिए.
that do not do something just because you can get paid for it. You will not enjoy, and results are not going to be fantastic if you're doing something
Manoj
just
Sharma,
because
sir.
you want to get paid for it. Okay, that's my personal take, of course. Okay. Now here's a word of caution. If you
Okay. So I was talking about we in India have to create lots of merit-based opportunities for our scientists to interact with the scientists of other countries, because this COVID has provided that opportunity to us. So the physical space has no meaning now. From the point of view, I'm just talking about a very recent phenomena, that is the Laser Interferometer Gravitational Wave Observatory. That is, in short, we are talking about the LIGO, and which is in talk on everyday science news. So this LIGO project, India is a very special location. By putting a LIGO detector in India, we will be able to identify far better than any other country that before the locations and the sources of the gravitational waves in the sky. This is done by looking at the delay in the time of arrival of the pieces of the signals at different locations. And India is near an ideal location to complement the detectors in Europe. I'm not saying that India will be only one, but we can get the signals fast and we can complement the detectors which are stationed at Europe, North America, and further detectors are going to be put up in Japan. So this is essential for telling the electromagnetic astronomers where the source was. So India has a lot of locational advantage, only we have to exploit. From Indian point of view, this LIGO brings to India existing advanced measurement technology and participation in developing the next generation of measurement technology, the part of quantum physics. So we have opportunity, only we have to identify where to strike. So LIGO is one of the things which our physicians, the faculty in the physics who are working in quantum physics, they can exploit, they can talk to the government of India science department, because we have to tell as a faculty. Nobody is going to come to us. We have to identify it. So the most enjoyable time for part was the brainstorming on how to incorporate science ideas into our movies also is very good. They give the idea. It is tremendously enjoyable and fruitful. That can popularize the sciences. The number of science movies are there, and which really generate the interest of the students and the viewers in the science. So if we accelerate our efforts to combine physics, another part, with the literature, like plays, poetry, usually with some sort of science connection, it may generate more interest among the faculty and the students. So this is not the entertainment pure, but it gives some kind of visual impacts if we combine these things with the literature, the science literature with that. So I wish you all a very fruitful faculty development program, and hope whatever you learn during this FDP, you will use the same for promoting the importance of applied physics amongst the students on one side and will enhance the research, but that is more important. It will advance or enhance the research, particularly the applied research, by taking the more research projects in the field. So thank you for inviting me and giving me the time to sharing my thoughts, and thanks for patience listening. So thank you very much. Wish you good luck for the rest of the days, for the rest of the programs. Wish you good luck for the successful of this program. Thank you very much.
Thank you
Thank
very
you
much.
very much, sir.
Thank you so much, sir.
Thank you very much, sir, for your kind appreciation and support.
Your voice is
Thank you.
very low. It's not audible,
Hello.
Purvi. You have to keep the mic near your mouth.
Hello. Am I
मैडम
audible?
आप अपना माइक थोड़ा सा और पास लेकर आइए अपना, वो जो स्पीकर
Okay.
आप
वाला
हाथ
माइक
से
है,
मुंह
हाँ,
के पास
इसको
पकड़ लीजिए तो शायद आवाज आए.
Okay. Am I audible now?
Low voice.
My voice?
Low.
A low
Low
voice,
voice.
but it is audible.
Oh,
Okay, keep
yes,
on
we can continue.
talking.
Okay. हेलो.
Hello.
हाँ
Yes.
मैडम बोलिए बोलिए.
अभी आ रही है ठीक?
बहुत
हाँ,
धीमी
Yes,
आ रही
yes.
है पर आ रही है.
कम आ रही है जी.
आप बोलिए तो सही कुछ है.
Yes, sir. I would like to welcome our today's keynote speaker, Dr. Sadhna Singh ma'am, Professor and Head Department of Physics, Barkatullah University, Bhopal. Dr. Sadhna Singh did her MSc in Physics from Barkatullah University with second position in merit list. She obtained PhD degree in 1990 from Barkatullah University on her work study of mechanical and dynamical behavior of compound semiconductors. She has been awarded Junior Research Fellowship MPCST Bhopal, Senior Research Fellowship CSIR New Delhi, and Research Associateship UGC New Delhi. She also worked at postdoctoral research level at Indian Institute of Technology New Delhi from 1994 to 2003. Principal investigator in prestigious Young Scientist Award, DST New Delhi, and Pool Scientist, CSIR New Delhi. During this period, she worked in collaboration with High Pressure Technology Division, National Physical Lab, New Delhi, and Bhabha Atomic Research Center, Mumbai. She is a recipient of MP Young Scientist Award in Physics in 1990, jointly given by MP Council of Science and Technology and Department of Science and Technology, New Delhi. She has developed multimedia CDs on course materials in physics for the purpose of classes in 40 satellite interactive terminals through EduSet. In addition, she has edited 3 books of MSc Physics, Mathematical Physics, Classical Electrodynamics, and Solid State Electronics. Dr. Singh joined Physics Department, Barkatullah University in 2007 as reader. From 2010 to 13, she has associate professor, and since 13, she is professor. Her research area of interest is mainly high pressure phase transitions, structural changes, and related behavior of solid state transitions in advanced materials. She has published and presented more than 200 papers in international journals. She is referee in many international journals. She is guiding several students of PhD, MPhil, and MTech, and supervised more than 50 students for PhD. She has completed many projects successfully from funding agencies, UGC, DAE, BRNS, DST, MPCST, etc. Presently, she is Head Department of Physics and USIC. She is Chairman of Board of Studies Result Committee, Academic Council, etc. Dr. Singh is a member of Academic Council of Sarojini Naidu Government College, Excellence College, and Maharani Lakshmibai College. BOS member of Satya Sai College, Bhopal. She visited many countries for academic and research purpose like Australia, Singapore, Mauritius, Japan, USA, etc. Dr. Singh has exposure of working in educational system like conventional universities as well as Premier Institute of India, IIT. She is member of IQAC, member of Academic Council, NEC, Chairman of Board of Study Physics, Coordinator, SAP, FIST, Departmental Program, Nodal Officer, Governance, Benchmarking Activities. And she is lifelong member of Indian Science Congress Association. I heartily welcome today's speaker and my guide, Dr. Sadhna Singh ma'am. She always there with me in my hard and good times. She is good listener of mine and always motivate me and guide me. Most welcome, ma'am.
Thank you, Dr. Purvi Bharadwaj. Thank you, Dr. Neetu Paliwal. And especially thanks to Dr. Petia, Vice Chancellor, Aisect University, now Rabindranath Tagore University. As the audience is mixed here from different streams, as I came to know, I have made my presentation relatively simple so that everybody will connect to it. Now I'm sharing my presentation. Is it visible? Screen?
Yes, ma'am. थोड़ा सा स्क्रीन प्रॉपर नहीं आ पा रहा है मैम.
Now?
Yes. Yes, ma'am, visible.
Full screen? Is it full screen now?
Visible है.
Visible है कि full screen है?
Yes, ma'am.
Full screen है. Visible है.
Okay, okay. Today's topic I have chosen high pressure phase transition in solids. High pressure studies are important because from deep down earth to planetary bodies, they all experience pressure. When we create or generate same pressure in laboratories or simulate in computer programs, materials are in same conditions as in deep earth or in other planets. So we can know the behavior of materials at high pressure and identify them. So it helps us to confirm their presence in deep down earth and planetary bodies. This is just one example of the importance of high pressure phase transition phenomena. Other importance I'll discuss. Contents which I'll cover in this presentation are given here: phase, stability of phases, phase transition phenomena, importance of high pressure phase transitions, importance of high pressure as well as phase transitions. How many techniques are there to explore these phenomena and what are the types? Maybe
पूर्वी मैडम आवाज नहीं आ रही है मैम.
मैसेज कर रही हूँ रुकिए.
हाँ, आप फोन कर दीजिए.
हाँ.
हेलो मैम.
हाँ. मैम आवाज नहीं आ रही है आपको.
नेटवर्क पूरा चला गया मैम की, वो भी नहीं आ रही, फोटो भी नहीं आ रही है और इसकी.
ओके मैम. जी जी. हेलो नीतू मैम.
हाँ जी.
वो पावर कट हो गया मैम, फोन से कनेक्ट कर रही हूँ.
ओह माय गॉड.
हाँ, सिस्टम वो लीव करना पड़ेगा ना, उससे करेंगे. फोन से करना पड़ेगा. 2 मिनट. हेलो।
हेलो,
यस मैम।
यस मैम आ रही है आवाज।
स्क्रीन विजिबल है?
नहीं अभी नहीं है, अब है, अब
यस मैम
ओके ओके ओके। वेरी सॉरी, लाइट नहीं जाती कभी, जस्ट फॉर 1 सेकेंड लाइट गई, सारा डिस्कनेक्ट हो गया है। इज इट विजिबल नाउ?
यस मैम।
यस मैम
Okay. Now I'll start. Okay. So I was discussing about high pressure phase transition phenomena in solids. Am I audible also?
Yes ma'am.
Yes, sir. Yes, ma'am.
Okay.
Yes, ma'am.
Okay. So these are the contents which I'll cover in my presentation today. So as I've already told that I have kept it simple so that persons from non-physics area also will understand. Importance of high pressure research. Whenever we start any research, first question, why? Why do we do this research? So importance of high pressure research, we can tune properties in solids without changing their chemical composition. When we apply high pressure, it can predict changes in earth after nuclear explosions. Materials face high pressure and high temperature at many places like diesel engine, jet planes. So we can simulate how they behave there when they are put under high pressure and high temperature. Here one interesting example I'm showing here, one beautiful example is formation of diamond in earth. The formation of natural diamonds require very high temperature and very high pressure. So most natural diamonds have ages between 1 billion to 3.5 billion years. Most were formed at depths between 150 to 250 kilometers. So whatever diamonds, they are so expensive and the hardest material ever known. Some materials show different properties when they are put under high pressure or high temperature and they transform from one phase to another phase, then they show altogether different properties from their parent phase. One example I am showing here, when amorphous boron nitride is kept under high pressure and high temperature, temperature around 1500 degrees centigrade and pressure around 7 GPa. It converts to cubic boron nitride. So cubic boron nitride is having properties altogether different from amorphous boron nitride. Cubic boron nitride is very hard material. Diamond is also hard material, but diamond is very expensive. So cubic boron nitride can be used at many places where diamonds are used. So it is used in cutting tool industries, blades, edges of machines, and so many places. After experiencing high pressure or phase transition phenomena based on high pressure or high temperature, materials convert to a altogether different phase. They show change in their brittleness, ductility, elasticity, strength, conductivity, and many more properties. We all know that we have to use materials from even tip to buildings. In buildings also we use material. So we should know the exact behavior of materials when they are put under high pressure or high temperature. In buildings also they bear so much of pressure. So at what number of persons they can bear this building. So these materials we study in labs and simulation in computer programs. So we can show it in advance that this material will behave at under high pressure and high temperature. It will bear this much of pressure or it will bear this much of weight, and how much its brittleness or ductility is going to be after facing this much of pressure or temperature. So we find change in many properties in materials after phase transition like brittleness, ductility, elasticity, strength, conductivity, and so on. If we study phase transition phenomena in various materials, this knowledge will help us in using them under high temperature and pressure or under the effect of electric and magnetic field. Now, before going in detail of phase transition phenomena, let us know what is phase. Everybody knows about it. In dictionaries, it is given the definition of phase is any stage in a series of events or in a process of development. But in scientific knowledge, we know any system or group of atoms may be homogeneous or non-homogeneous. So homogeneous part of such a system is called phase. This phase is characterized by thermodynamic properties like volume, pressure, temperature, and energy. Phase is always physically distinct, mechanically stable, and chemically homogeneous part of any system. And two phases can be distinguishable from each other if they form different composition or different crystal structures. Now comes a very important part of phase transition phenomena or high pressure, high temperature study, that is stability of phase. Stability of phase is very important and it is directly related to energy. A stable phase is always associated with minimum of energy under given thermodynamic conditions. If the phase is present in the local minima instead of a unique minima of free energy, the system is said to be in a metastable stage. Local minima here I'm showing here that if a system is at one position, it is clearly seen that it is unstable. But in 2, it is relatively stable than 1 and 3 position. So this is local minima where it is stable, but it can be further pushed. So when it is further pushed, it will go to 4th position, and 4th position is the most stable, that is minimum of energy. So one local minima, this will be corresponding to 2nd position, and lowest energy is corresponding to 4th position. Now, what is phase transition? When we talk about high pressure or high temperature, it is not complete without its behavior under critical conditions. Critical condition, critical temperature, critical pressure is phase transition pressure or phase transition temperature. A material or solid undergoes a phase transition when a particular phase becomes unstable. A phase transition occurs when one or more phases, that is parent phase. Starting phase is always known as parent phase. Changes to one or more phases, that is product. Whatever we get after phase transition is product phase. When any variable acting on system like temperature, pressure, electric or magnetic field is varied, the free energy of system changes smoothly and continuously. If with such variations of free energy, if the structural details of phase are changed, phase transition is said to occur. Phase transition involves changes in composition or crystal structure or electronic structure, and they are associated with change in many properties. During phase transition, free energy of the system remains continuous, but thermodynamic quantities like entropy, volume, here I am showing a phase transition phenomena in pressure-induced phase transition. G1 and G2 are the two energies. Here G1 is the first material with which we have started our journey. So G1 under pressure, when we put G1 under pressure, it converts to G2. So up to phase transition, it is this curve is real, and after phase transition, this phase is real. G2 before phase transition, this G2 curve is hypothetical, and after phase transition, this G1 extended curve is hypothetical. At the phase transition pressure, we can see with these two compounds, these two phases, that there is a volume collapse at the phase transition pressure, and this collapse is always associated with phase transition pressure, and it shows that this phase transition is of the order of first order. Pressure-induced phase transition result in an increase in coordination number of neighbors. When we apply pressure, the material goes under compression, and whenever it goes under compression, we will get a less volume or volume collapse, and number of neighbors will be more. Negative volume change, but in thermal, but when we apply a temperature, material expands and we get a positive volume change. So here I am giving one example of phase transition under pressure. We take guessed energy, and G is equal to U plus PV minus TS is given here. U is the internal energy. For this U internal energy, we take our potential model with interatomic interactions, which includes Coulombic interactions, three-body interactions, overlapping repulsive interaction, covalency interactions, zero-point energy interaction, and many more. We can include more interactions depending upon the compound. If compound is covalent, we include this covalency energy. If it is not covalent, we drop this. So and so on. We simultaneously calculate energies of both the phases. First is real phase, which is associated with, we can associate with G1, and second one is associated with G2, that is hypothetical phase. So these two energies we take and give these energies, and then we take difference and we plot them at the pressure where this delta G difference in these two energies becomes zero is the phase transition pressure. First and second order derivatives of free energy, they show first order phase transition and second order phase transition. When we take first derivative of these free energies, the quantities given by first derivative gives you energies, volume and entropy. If they show any discontinuity at phase transition, this is first order phase transition. If we take the quantities given by second derivative of this energy, volume, thermal expansivity, etc., or specific heat, if they show any discontinuity at phase transition, then our order of phase transition is second. Here I am giving a little example of what happens when phase transition occurs. This is under Zinglet structure and goes after phase transition to rock salt structure. We can see here that at the phase transition pressure, there is a rearrangement of atoms in structure. So earlier they were arranged in Zinglet structure, and at the phase transition they rearrange and they take a phase transition to NaCl structure. We can study phase transition phenomena or high pressure, high temperature studies. There are many advanced techniques. In laboratory, we can use many theoretical as well as many experimental techniques are available. Some example I am giving here. Many theoretical methods are available for the study of phase transition phenomena. Regular phenomenological modeling that started with rigid ion model, then with advancement we got two-body model, then three-body interaction potential model. Now we have DFT calculations. For these sophisticated calculations, we simulate conditions of phase transition phenomena, high pressure in computer programs. For this, different codes are available. These codes, some are free downloadable codes and some are very expensive. So some codes I'm giving here, Quantum Espresso is free downloadable, and Win2K we have WASP and Crystal, NanoLab, ATK tool, Material Studio, CASTEP. There are so many codes are available through which we can study our materials, whatever we want. Now, there are many experimental techniques are also available. Experimental techniques include anvil cell, diamond anvil cell method, tungsten carbide method. The first diamond anvil cell was created in 1957-58 in order to achieve highest pressure without breaking anvils. If we increase pressure, so there is a possibility of breaking anvils. So they used hardest ever known material, diamond, single crystals of diamond. Its optical transparency makes it to stand out from other pressure devices. Properties can directly be observed in sample under pressure. So diamond, they took two diamonds and pressed sample between them, so that the contact area was very low. It works on simple principle of pressure is equal to force upon area. When we use very low area, the unit sizes for diamond anvils are 100 to 250 microns. So a moderate force can create much greater pressure. So it is simple to create a major pressure using diamond anvil cell. For keeping sample, they used a soft pressure transmitting medium. This medium should be highly pressure transmitting medium, so that whatever pressure they are taking, maximum they should transfer to sample. So some gases can be used as helium, neon, liquid, some silicon, oil, etc. Solids salt may be taken. So diamond anvil cell was a method with which even it is used, very sophisticated, and it is a very small apparatus. So it is used in many places, many labs, BRC and NPL. So many labs have this diamond anvil cell method. Now I'll come to cubic press. This is a huge device. Cubic press is huge device. It is kept in one room, full room. It covers full room, and it is kept in the National Physical Laboratory in Delhi. I worked on this also. So they have this apparatus is so huge that you operate it from outside of the room, from glass, and we have remote outside, and we operate from there. So that sometimes sample also bursts, so you keep yourself safe and you keep yourself outside of the room. There are 6 arms. They all together press material, kept in soft material. The soft material they used pyrophyllite, which is highly pressure transmitting material and very soft material. A sample is kept inside this, and 6 arms pressed it together, and we take readings from outside of the lab. Diamond anvil cell consists of 2 gem quality diamond crystals with polished faces mounted on the ends of 2 pistons, which can be driven together by means of a lever and spring assembly. Diamond has been known as the hardest substance with transparency to X-rays and visible light. With DSC, one thing is added in advantage is that we can assess its structure at the same time when we are pressing it, because it is fully transparent to X-rays. In high pressure studies, various types of diamond cells are used: NBS cell, Bassett cell, Mao-Bell cell, Siasen-Holt cell, and etc. Now, shock wave technique. This extended the pressure range shock wave in solids are produced by an impact of a projectile on the sample or by detonation of an explosive in contact with it. The result is the introduction of a step pressure that propagates through the sample. So dynamic compression methods are required to generate more pressure to understand the composition and physical states of the deep interiors of the earth. So in a dynamic method, these methods allow compression on time scales. That time scale is ranging from nanoseconds to microseconds. They are dynamic method. In DAC static methods, we keep sample under pressure for a longer period, so there are thermodynamic conditions are maintained for a longer time. But in dynamic methods, shock wave method, the thermodynamic conditions are not maintained, because it is a pulse is sent for a fraction of second. So, but it creates a larger amount of pressure. So here again, cubic press Tracy Hall, it is 200 ton, as I have already told you. It was a huge machine. Now I'm talking about some types of transitions in AB compounds, binary compounds. Here I'm giving some examples how they behave under pressure. Whenever we keep initial structure compounds under pressure, they transform to B2, CSCl, body-centered compounds. The examples are NaCl, CSCl, RBCl, NABr, KBr, etc. Whenever we keep CSCl structure compounds under temperature, they transform to B1 structure, that is NaCl structure. The examples are CSCl, NH4Cl, NH4Br, etc. Whenever NaCl structure compounds are put under temperature, they transform to Woodside structure. And whenever B3 structure, that is single structure compounds, are put under temperature, they transform to B23 structure, for example, AGI. NaCl structure, when we put pressure, we apply pressure on some NaCl structure compound, they transform to B9 structure also. Here, one example I am giving here, AGC. Some B3 compounds, third, fifth compounds, compound semiconductors, gallium arsenide, gallium nitride, gallium phosphide, gallium antimonide, and indium compounds. When they put under pressure, they transform to B1 structure, that is NaCl structure. Now here, from my one latest paper, I'm giving some results here. That is analysis of structural phase transition and thermoelastic properties of alloy of our rare earth compounds. Here I have taken some rare earth compounds, LAS and PRS, and kept under high pressure. And results are here. For LAS, PRS, we mix these two compounds with compositions from x is equal to 1 to 0.75, then change to 0.5, 0.25, and 0. So starting from this point, LS to PRS, we have shown here, we are showing here the different phase transitions at 0 temperature. And associated volumes are also given here, this for same compositions. So before phase transition, these are NaCl. From this to this, they are the graphs of NaCl structure, and after phase transition, these are the B2 structure. So at the phase transition pressure, we see this volume collapse associated with all these phase transitions. Different phase transitions are given here, and associated volume collapses are given here in the second graph. When we repeated this all exercise, keeping temperature, including temperature also of room temperature, then we saw that the phase transition pressure, which was 28.5, it has reduced to 27.25. So when we apply temperature also, we can reduce the pressure of phase transition from a small amount. So similarly, it is given for all the compositions given here. 22.90 has become 22, and here also we see that the different volume collapses are seen here for different compositions. So this was one example from my work, which was published in 2020 December. So I think some interesting facts I have shared with all of you. If anybody wants to know anything, then he or she is welcome.
If anybody asks a question, please put it on a chat box. Are there queries from participants?
Webinars are very good. If you want to hear something, it is your freedom. You can take part. If you are not interested, virtual meetings are very good, as the interesting person can attend, and which is of not interesting, he can hear. He or she can hear.
I think I have not got any question from participants. So Neetu ma'am.
ये मैम बहुत प्राउड मोमेंट है मैडम, आप हमारे बीच में आए। अब बहुत जल्दी मैडम को ऑफलाइन भी यूनिवर्सिटी बुलाना चाहते हैं मैम। बहुत बहुत थैंक यू।
बिल्कुल, ऑफलाइन जैसे ही एक्टिविटीज चालू होंगी वैसे ही मुझे भी अच्छा लगेगा कि मेरी 2 स्टूडेंट्स वहां पे हैं।
यस मैम,
इट फील्स लाइक होम।
जी, थैंक यू सो मच मैम, थैंक यू सो मच।
ओके, थैंक यू एवरीबॉडी, थैंक यू फॉर लिसनिंग my presentation.
Thank you, ma'am.
For your presentation.
Okay.
Ma'am, Neetu ma'am, vote of thanks.
हाँ, आप दे दीजिए मैम जी। हेलो
हेलो, आवाज आ रही है मेरी?
हाँ, आ रही है, बिल्कुल आ रही है।
ठीक है। It's my privilege to have been asked to propose a vote of thanks on this occasion. I would like to thank our Honorable Vice Chancellor, Dr. Brahma Prakash Petia, sir, to his precious time for this faculty development program in recent advancement in pure and applied physics. On behalf of Rabindranath Tagore University, I extend the vote of thanks to our today's speaker, Dr. Sadhana Singh ma'am, who spared time from her busiest schedule to share the findings and opinions with us. Today we had an opportunity to hear your thoughts, and this will surely be going to encourage us in our future events. I extend my vote of thanks to our Dean Faculty of Science, Dr. Neetu Paliwal, our HOD, Ms. Jyoti Rawat ma'am, our faculty members and participants. It is my privilege to offer thanks on this occasion. I extend my vote of thanks to our technical department, Mr. Raman sir, Iyer sir, Mr. Mangesh sir, and Mr. Bhagirath Ahirwar. So thank you so much, all of you.
Thank you. Thank you.
Thank you.
Okay. Okay. Thank you.
Thank you so much, ma'am.
Okay. Thank you. Thank you. Now
Thank you.
we can leave.
Ma'am.
Thank you.
Thank you,
Okay.
Sagar.
Okay. Okay.